So let's switch gears and try to understand machine learning primer and supervised learning within that. So here we go. Whenever you build a machine learning algorithm, you need access to data. And this data is called as historical data or the past data. So you have historical data or the past data. This data, if I were to pull it separately and show it to you, would contain your features. And if it's predictive modeling technique, you will also have your label, which is output variable 1. And then say you have your input variables. And let us assume that we have 10,000 observations and we want to predict whether a person will default on the loan or not default on the loan. And given the various inputs such as age, gender, education, income, right? There could be a lot of other inputs, but we are confining our discussion only to the first 4 inputs. So you have data. Once we have the data, when you build the model, especially when you build a predictive model, after building the model, when you give it to the customer, when you give it to the customer would ask you on what is the accuracy of the model? How accurate is your model? Is it 80% accurate or 90% accurate, or is it, what is the accuracy actually? Then given that context, you obviously cannot say that, hey, use the model in the real world, and then you figure out what is the accuracy of the model. You cannot obviously say that. So what you'll tell to the customer is that, customer, you have given me the data, which had 100,000 or 10,000 observations. Out of that, I've split the data into training data set and test data set. And assume for now that your data set was balanced. Assume for now that your data set is balanced data set. If your output variable is balanced, that means say 40, 60 or 50, 50%, right? 50% of the entries were default and another 50% were not default. If you have a balanced data set, then when you split the data into training and test, you do a random split. You do a simple random sampling. And then you split the data into training and test. And usually, people have 80% of data in training and 20% of data into test. Usually. You can have 70%, 30%. You can have 60% in train and 40% in test. You can have 50% in train and 50% in test. 90% in train and 10% in test. Yeah, so on and so forth. Okay, so when you split your data randomly into training and test, you need to remember that within the training data, the more the data you have, more are the patterns that your model is going to learn. For instance, since you have now split the data into training and test, let me pick up this. Let me draw the table here or the data set. output variable and input variables. And since you have randomly chosen 80% of observations, say you have row number 2, row number 4, 5, 7, 8, so on and so forth. When you count these observations, you get 8,000 observations because 80% of 10,000 is 8,000. So say you have 8,000 observations in the dataset. And then you build your model. Building the model means learning the patterns between your output variable and your input variables. That is what building the model means. So if the age is 32, gender is male, education is graduation, income is say $10,000. So probably person of this kind will not default. So this pattern is learned that, if age is 32, gender is male, education is graduation, income is $10,000, people will not default. People of this kind will not default. So your model has learned that pattern. In that way, for every row, your model will look at, machine learning algorithm will look at the inputs and what is the corresponding output, and it will learn the patterns in your dataset. Once it learns the patterns between your output variable and input variables, it would come up with an equation. So you build a model, and this model would actually use to test, right? So when you say build the model, output variable is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. If it's a regression model, we will talk about all these things in thorough detail, right, at a later point of time. This is your regression model. Then, if you have, instead of 8,000 observations, say 20,000 observations, the more the data you have, more patterns your model will learn. More relationships between your output variable and input variables is what your model is going to learn. And your model is going to capture those patterns in an equation like this. Okay, your model is going to capture the patterns in an equation like this. Then you proceed further and test it on your test dataset. So let me once again draw this representation. Output variable x1, x2, x3, x4. And then whatever rows are not part of training data, those will be part of test data. For example, you don't have row number 1 in training dataset. So row number 1, you do not have row number 3. You don't have row number 6, so on and so forth. When you count 1, 2, 3, etc., you get 2,000 observations. When you test your model on the test data, the point that I'm trying to drive is you take the inputs, age, gender, income, education. You substitute these in the prediction model, and then you get the predicted value. Predicted values are represented using a hat on the top, like y hat. And then you'll have the actual values as well. It means here, probably it says that person has defaulted, right? That's the actual value. So when you take your inputs here and substitute in your model might say that, hey, person has the first person or the first row will default. Your model predicts that this first person will default. And the actual value here also says that person will default. If the predicted value and actual value, when you try to compare, if they are the same, that's correct prediction. Let's take the second rule. You once again take your inputs, age, gender, income, educational, educational income, etc. Substitute in the equation, and then you get a predicted value. Say you get a value which says person will default. But when you look at the actual data, say the actual data says that person will not default. Is this a correct prediction? No, it is incorrect prediction. In that way, for all of these 2000, you get to know how many are correct and how many are incorrect predictions. And if you want to calculate the accuracy on the test data, you just look at how many times your model has correctly predicted. Number of correct predictions divided by overall predictions. Okay, how many times your model has correctly predicted divided by overall predictions. Sorry, I keep getting some ideas and I don't want those ideas to be, forgotten. Very quickly they come and they leave. So I always have a book and a pen even while I sleep. Right? I make it a point to quickly wake up, somehow scribble it and then leave it there. Okay. So here you have accuracy, which is number of times you have correct predictions divided by the overall predictions. Say you have 1400 correct predictions out of 2000. Assume, example, 1400 out of 2000. That would give you an accuracy of 70%. So you get a test accuracy of assume 70%. You can be more confident about this value. You can be more certain that, test accuracy is 70%. You can be more certain, more confident about this number when you communicate to the customers, end users. When you have more data in the test, you can say that, here I've tested on more data. So with confidence, I can say that accuracy that we can achieve is 70%. So the reason why I'm explaining this aspect is because I want you all to understand that when you split the data into training and test, the more the data you have in training, more patterns your model will learn. More data you have in test, more confident would you be with the accuracy. This is how it works. Okay. So let me remove this and then draw that back. Shouldn't be an issue. What happened? Okay, next. You probably are not happy with this accuracy of 70%. What should you do then? Maybe customer might have told you that if I do not get an accuracy of 90%, I would not care about your model. I would just put that into a trash. bin. So you, at this juncture, would go back with this information that accuracy is 70%. With this information, which you received by testing on the test data, you receive an information that accuracy is 70%. With this information, you go back and then you tweak your hyperparameters. You perform hyperparameter tuning. Okay, you perform hyperparameter tuning. What does that mean? Every algorithm would have a bunch of hyperparameters. We've already discussed this enough times, right? As part of our unsupervised learning also, you would have certain hyperparameters. As part of supervised learning also, you will have a bunch of hyperparameters. These are the options that you might want to tweak, change, and then rebuild your model. And this time, see, you got, and then you rebuild your model, and when you test it on the test data, assume that you got an accuracy of 80%. Okay, this is say model 2. And when we have built model 1, say we got an accuracy of 70%. You're still not happy because customer told you that, hey, I need by hook or crook 90% accuracy. So you probably would go back with this information that now the accuracy is 80%. With this information, you go back, again, tweak your hyperparameters, and then build your model, and once again test it on the test data. When you do that, probably this time, model 3 gave you an accuracy of 92%. Maybe you're now happy that, yes, I crossed the limit set by the customer. Customer told, you know what, I need minimum 90% accuracy, and then there we go. I could give the customer an accuracy of 92%. However, I also want you all to remember that. Or let me draw a small parallel of this explanation with students. Suppose you have 3 students, student 1, student 2, and then say a student 3. Say student 1 has an accuracy of maybe 70%, or sorry, student 1 has a percentage of 70% in their school. Student 2 gets 80% and student 3 gets 90%. In their final exam, all 3 are in the same class. I mean, they belong to the same standard. For example, everyone say was in 10th standard as an example. When can you say that student 3 has done an exceptional job or student 3 has got the highest percentage? When can you say that? Can I put it in this way that, you know, student 1 studied for the exam on state syllabus. Student 2 had CBSE syllabus, and student 3 had ICSE International Cambridge syllabus. 3 of them have studied on a different syllabus, and then 3 of them would have probably different exam patterns. if that is the case, we cannot compare the percentages obtained by these students. You cannot compare and say that student 3 has received highest percentage. You cannot say that. Why? Because the underlying syllabus on which each of these students have prepared themselves for the exam is pretty different. So you cannot compare these percentages. On similar lines, my dear friends, if these three models are built on different data sets, then it will not work. You cannot compare the accuracies if these three models are built on three different underlying data sets. The reason why I'm explaining you about this is because I want to drive a point here, and everyone has to pay heed. Pay attention, please. If you have Python code, what do? You load the libraries, you import the libraries. Then you load the dataset. Either it's a CSV file or Excel file, or from some database, you're trying to pull the data into Python. Then you perform data pre-processing or data cleansing. Once you're done with data cleansing, you perform model building. Okay, so even before you build the model, you split the data into training and test. So you split the data into training and test. Then you build the model on the training data, and you evaluate your model on the test data. And you deploy the model, so on and so forth. Here, say you build the model, you split the data, you build the model on the training data, tested on the test data, and then you got an accuracy of 70%, assume. If you're not happy with that, you go back with this information and tweak your hyperparameters. And then once again, build the model. And then, in model building, you actually tune your hyperparameters here. Hyperparameter tuning happens here. But when you tune your hyperparameters, sometimes when you change your hyperparameters, you might want to run the code from here onwards, that is model building onwards. If you do that, wonderful. But in most practical scenarios, you will have an option to run the entire file. Okay, execute the entire file, or you'll have an option to execute each line. Okay, you will also have an option to execute each line. If you execute the complete file by tuning your hyperparameters here, when you run the entire file, you load the libraries, you load the data set, you perform the data cleansing, and then you split the data. And since you're doing a random split into training and test, each time you split the data, you would get different observations in your training and obviously different observations in the test, because whatever observations are not part of your training would be part of your test. Once again, if you say you got an accuracy of 80%, once again, with this information, when you go back and tweak your hyperparameters and once again build your model, if you were to execute the complete file, once again, you load the libraries, load the data set, data cleansing, split the data, build your model on the training data, and once again test it on the test data. So when you split that, you might end up getting altogether different observations in the training data set, and whichever are not part of these, whichever observations are not part of training would be part of test. So that means you cannot compare the accuracies. When can you compare the accuracies? Only when the underlying training data remains the same each time you tweak your hyperparameter and build your model. Each time you tweak and build your model, if the underlying training data set and test data set remain the same, only then can you do a comparison between different models, accuracies of different models. For this, to achieve this, we have something called as random state. Random state or random seed. Here, within the brackets, you just mention some number. Say you like 17 and you give 17. So what happens is when you run the file, libraries are loaded, dataset is loaded, data cleansing, and next it looks at this. It stores this number in memory. It will store that. It will bear that in mind. And then it will split the data. The moment it splits the data, all these observations like 2, 4, 5, 7, 8, so on and so forth, which are part of training data, that information will get stored in this. This is like an object. This number is like an object. And all these observations, 1, 3, 6, so on and so forth, should be part of your test data. And this information gets stored in this number 17. So whenever you tweak your hyperparameters and when you once again run the entire file, the moment it comes to this line, it will figure out that random state is 17, and 17 holds the information that these observations should be part of training and these observations should be part of test. And then you build your model, evaluate your model, job done. Once again, if you were to tweak your hyperparameters and run your entire file, once again, when it processes each line, at this line, it will look at 17 and understands that, okay, 17 should hold all these values in training and all these values in test. And then it will proceed further. Okay, in this process, how many more times you run, the underlying training and test data set will remain the same because our information is available in this. If you want 171, give 17163, give. Whatever number comes to your mind, you can give, friends. That number is just like an object, which will hold the information that all these variables should be part of, observations should be part of train. All these observations should be part of test. Okay. So assume that you have used random state and assume that you can compare the accuracies of these three models. And you figure out which model has given you the highest accuracy and you save that. So say there's one specific model, you stored the model parameters. All these are called as parameters. And what were the hyperparameters used in the model? Which model you have used? You store all of those alongside the details that test accuracy was some number, say it was 92%. You should not stop here. Some student has got 92% in test. Fine. Was that by fluke? Or did that student actually, when that student appeared for the internal exams, pre-final exams, the student has in pre-final exams also got around 90%. We don't know. We need to figure out. So what you do is you take the model that you've built and test it on the training data. Now you might argue with me and say that, hey, Barani. Since we have built the model on this training data set, when I test it on the same training data set, wouldn't I get 100% accuracy? Not really. Okay, not really. So it's like this, friends. Let me here explain that if you have, say, an output variable and input variable, so you have 4, 2, 6, 3, 9, 1, 10, 5. In that way, say you have data. Okay, say you have all these observations. And then when you build the model using this data, you get an equation, y is equal to 2x. So you take the first row, you take this 2, substitute in the equation. You have built a model, friends. Building a model means you get a math equation, simple. So building machine learning model means nothing but math equation. If you substitute this input 2 in this, 2 into 2 is 4. So the predicted value will say it is 4. And the actual value here also says 4. Do you have any error? No, you don't have any error. Take the next observation. 3, substitute in this. 2, 3, 6. That's your prediction value. Actual value is also 6. When you subtract these, you get error as 0. Then go to the third row. When you substitute 1 in this, you get the predicted value as 2. Actual value is 9. And then you have another observation. You have 5. When you substitute this input 5, you get 10 as a predicted value. Here the actual value is 10. So in this, are you getting 100% accuracy? Not really. For this observation, you're getting wrong result. Predicted value and actual value, when you subtract, you get an error of 7 or -7. If it's 2 minus 9. I mean, that minus sign doesn't make sense because I'll explain later in a moment. So what does that mean? The model equation that you get would try to capture the patterns in your data in a generic manner. You cannot get an equation or a model which will learn all the patterns equally well. That cannot happen, right? Because for all these observations, you have a single equation. So you're forcing a single equation to capture the patterns of your underlying data. So all these 8,000 observations patterns would be captured using this single equation. You cannot be rest assured that this single equation captures equally each and every observation, and on each and every observation you'll get an error as 0. You cannot assure that. Hence, what we are doing is, once you build the model, you're also testing on the training data. It's like you're testing your student on pre-finals, right? To see whether the final exam result is a fluke or is it based on some kind of real hard work that is being put in. So when you test on the test data, training data, you get training accuracy. Say here you got a training accuracy of 93%. Both are very good accuracies, high accuracies, and both are close to each other. So if both training and test accuracy values are going to be high, and close to each other, you say that this is a right fit model. However, when you build your model, assume that you got very high training accuracy, but when you tested your model on the test data set, you got a very low accuracy. Then this kind of a scenario is called as overfitting or variance. This is something like this. You prepared on your exam question papers, sample question papers to such an extent that you by-hearted the patterns. And you know that in the question, if it says Ram and Shyam, automatically the answer is A in multiple choice questions. If you by-heart to this extent, what happens in the real data set or in the final exam? If it says Sita and Geeta, you'd be like confused. Ram and Shyam, I know that option is A. Sita and Geeta, I really don't know. So your model will start giving you less results in the on the test data set. This kind of, okay, another thing. If you get less training accuracy, that means you prepared on your sample papers, but when you took your exams on the sample papers, you didn't do well. If you did not do well on the sample papers itself, then how would you do well in the main exam? So when you test on the test data, test accuracy also will be less. This scenario is called as underfitting or bias. You're underdoing, you're not preparing well, you're not training well. So obviously in the final exam or on the test data, your model will give you less results. Would you have a scenario where training accuracy is less and test accuracy would be high? Student did not do well at all in the pre-final exams, in the previous exams, and on the sample exams, he or she has done in a very poor way. But in the test, final exam, they've got gold medal. Would that happen? Until and unless the person seated before you or adjacent to you has really did well, you would not know that, right? So given this context, that scenario of training accuracy less and test accuracy high doesn't exist. So we can straight away rule out that. Back to our discussion. When you have scenarios where you have overfitting, variance, or underfitting bias, you need to fix that. Only the right fit models are preferred. How do you fix that? Using something called as regularization techniques. Every algorithm, every prediction model technique, every supervised learning algorithm will have regularization techniques. Mostly the hyperparameters, a few of these would be our regularization techniques. A few of the hyperparameters would be regularization techniques mostly. But not all hyperparameters are regularization techniques. A few of those would be regularization techniques. And you'll have exclusive regularization techniques for different algorithms. Given this, overfitting or variance is a big problem, friends. It's a very big problem, actually, overfitting or variance. Underfitting or bias is not a big problem. For underfitting or bias, of course, regularization techniques exist, but then you just increase the amount of data that you have, you perform proper feature transformation, feature engineering, and your results will be fixed mostly through proper transformations, etc. So that's not a big problem, but overfitting or variance is a big problem. You need to tweak a lot of regularization techniques to determine what is best. Okay, so this is one side of the story. The other side of the story is that you have two sections of data scientists with two different schools of knowledge. One school of thought or school of knowledge says that you split your underlying data set into training and test. Build your model on the training and test it on the test data. And then probably you get an accuracy, say if you get a less if you get an accuracy of 70%. With this information, you go back and tweak your hyperparameters, again build your model, again test it on the test data. This time probably you got an accuracy of 80%. With this information, you go back, tweak your hyperparameters, again test it on the test data. Maybe this time you got an accuracy of 92%, and you're saying that the model accuracy is 92%. But a few data scientists at different school of thought folks started arguing, and they told that, you know what? This is called as information leak. What do you mean by information leak? Your students are preparing for the exam. They come and take the main exam. Say they got 70%. If you give them a chance to go and prepare well and then come back and take the exam on exactly the same data set or exactly on the same paper, obviously their results will improve. Again, with this information, if you send your students back and if you say that, my dear students, dear students, you'll have the same exam paper, go prepare and come back. If they once again go back and prepare and once again come back and take an exam, probably they got 92%. But is this foolproof? Does this mean that that student is really worth 92%? Or just because you have given multiple chances for the student to go back, prepare well and come back and take the exam, is the accuracy increasing? We don't know, right? We really don't know. So certain data scientists started arguing that this is called as information leak. And to counter that, they have come up with a solution. And the solution is to split the underlying data set into training, validation, and test. So you have training data set, validation data set, and test data set. And here, once you build your model on the training data, you get this equation. Take this equation and test it on the validation data set. You don't test on the test data, you test on the validation data set. And then validation data set, once you test it there, say you got an accuracy, validation accuracy of 70%. So what do? You go back with this information, tweak your hyperparameters, again build your model, and then test your model on the validation data. Maybe this time you get an accuracy of 92%. So probably you're happy with this accuracy. Once you're happy with this accuracy, then what you do is you test that model on the test data. Now you test on the test data set. And whatever test accuracy you get here would be the final accuracy. If you get, say, 90%, then that's the final. This should be like the final data set which your model is seeing for the first time. And this is what you communicate to your end customer. That, dear customer, this is accuracy that I've achieved. Okay, this is how it works. And once you get an accuracy of 90%, then what you do is, you're not done yet. You record the hyperparameters and the model parameters, which have actually given you 90% test accuracy. When you tested, you got 90% accuracy. Record those hyperparameters and the model parameters, and then retrain using the same hyperparameters and the same models, same model that you built on the complete data set, then combine the data set. That means you get back to your historical data set. Take your complete data and then build a final model. You already figured out which model, what hyperparameters give you the best results. So you build the final model, and then you deploy this final model in production. And let your customers start using this deployed model for future data. Whenever there are new customers, like, 10,001th customer, you take the age, gender, income, education, put that into your final model, which is deployed in production, and then you get the results. This is called as inference phase. Means your deployed model is used for inference purpose. Okay. One another thing is, if you have millions and billions of rows to deal with in your data set, then usually people take 98% into train, 1% into validation, and another 1% into test data set. This is called as a thumb rule. Thumb rule means something which is not universally accepted, but most people go with this rule. That's called as a thumb rule. If you have, say, 10,000, 20,000, 30,000 in that way, again, there's no defined rule as such. Then people split the data set in the ratio of 60%, 20%, and 20%. 60% training, 20% validation, and 20% test. If it's only training and test, then usually they go with, if you feel that, hey, I would just have training and test. I don't want to have validation data set. Validation is also called as development data. Okay, then you usually have 80%, 20%. But again, if you have exorbitantly high amount of data, then it's 98% training and 2% test. These are a few thumb rules that you might want to bear in mind. One another thumb rule that makes a lot of sense here is that when you have machine learning algorithms, which have huge number of hyperparameters, many hyperparameters, that means you need to do a lot of experiments. If you're going to end up doing a lot of experiments, then you should split your data set into training, validation, and test. Okay, training data set, validation data set, and test data set. If you have less number of hyperparameters, then you'll have limited experiments to be performed. In this case, you're going to have just train and test. You can have just train and test. Okay, these are a few additional thumb rules that one might want to bear in mind before proceeding further. So this concludes effectively the high-level overview of a prediction model. Right? Prediction model, machine learning, supervised learning techniques at a very high level follow this kind of structure or a flow. Okay, one more thing, what people also do is once a model is deployed in production, once you keep getting back the results, you also write it back to your database, all the prediction results. You create another column, keep storing that. Why? Because eventually, if your model accuracy keeps on decreasing, that's called as model drift. Then you might want to retrain your model using the new data that is captured. And based on the prediction and actual values, you get to know whether your model is good or bad. And yep, so this is a prime reason. You also have something called as concept drift, data drift, etc., that would be discussed as part of a different discussion.